Hi there, this is Dr. Maxwell, and this lecture is on section 4.4, which talks about the mean value theorem. Very important theorem for math majors to know and math minors. It's a little tricky, but this example 0 maybe will help you understand what it's saying. So, suppose one day Dr. Maxwell was driving to Florida and she decides to take this toll road. Speed limit, that might be important. When I'm doing a word problem, this is sort of my process. As I'm reading it, I write down um, everything that looks kind of important. I pass this first pay point at 10 a.m. and then I drive for 1.5 hours. So that means at 11:30, I guess, I come to the second pay point and I've gone 120 miles. Okay, does everybody understand the setup? Here's this little car. I'm in here going 120 miles from the first toll booth to the second one, and I did this in 1.5 hours. And I didn't think anything about it. However, about 2 weeks later, I got a speeding ticket in the mail. What? How did that happen? Your job is to explain it. Well, here's something important that maybe Dr. Maxwell didn't know, that these toll roads these days, you have to have like this card in the car that gets scanned. Sometimes it's up on the dashboard, sometimes it's down here. But the toll road scans it, and maybe it also scans the time. So how did somebody know I was speeding? Well, what was my average speed? Average speed, remember, is the change in position. So this would be, let's just call it T2 minus T1 over the change in time. And we already know what the change in position was. It's 120 miles over the change in time, 1.5 hours. So put that in your calculator and find that my average velocity, if you want, it is speed in this case because it's positive, but technically perhaps we should call it velocity. My average velocity was 80 miles per hour. Okay, so what does that have to do with the mean value theorem? Well, we know the average velocity is 80 miles per hour. The mean value theorem tells us this. At some point in this interval, between, at some point between, say, 10 a.m. and 11:30 a.m., my average speed or velocity, my average velocity was equal to my instantaneous velocity. That's the whole idea behind the mean value theorem. And remember what the average velocity is. This is the slope of the secant line. And what is the instantaneous velocity? This is the slope of the tangent line. Let's use a different color. And how do we find the slope of the tangent line? Well, that was the derivative. So there is some time c, we call it c, the slope of the secant line equals the slope of the tangent line. That really is what we're talking about. Okay, on to the real deal. The mean value theorem is a more general case of what is known as Rolle's theorem. And you'll come across these again in upper level math courses. We're just kind of talking about them now. It's good to understand how a theorem works. You have conditions. This is how a theorem works. You have conditions that must be met. And when they are met, we get a certain result. So in this case, what we need is a function to be continuous on a closed interval, a, b. It also has to be differentiable on the open interval. This is b, a, b. So there's two conditions. It has to be continuous and it has to be differentiable. And if at some point in this interval we have this situation, which you can see here in the graph, f of a equals f of b. Doesn't necessarily have to be on the x-axis. It could be somewhere else. There's a lot of places where that could happen. But if that happens, then there is going to be at least one number c such that f prime of c equals 0. In other words, if you think about this, the slope of the secant line joining a and b these 2 points, a, f at a, and b, f at b. Well, what's the slope of a horizontal line? It equals 0. So what we're saying, at some point in this interval, the instantaneous rate of change, which is the tangent line, is going to be equal to the average rate of change, which is the secant line. And that's why we say this. At some point, the derivative equals 0. The slope of the tangent line equals 0. So here's what we're going to focus on, the mean value theorem. So the conditions are the same. You need to be continuous on the closed interval. You have to be differentiable. That means f prime exists on this open interval. And if that's the case, then it's always true that, you see, here's my secant line. Whatever this slope is, well, it's given by this expression here. At some point, there's going to be a c, so that the slope at c equals the slope of the tangent line, of the secant line. And I'm trying to emphasize this because when you look at this expression here, that can be kind of meaningless. But remember, f prime at c, this is the slope of the tangent at x equals c. And we're saying at some point that will be equal to the slope of this secant line. And in terms of rates of change, it tells us at some point the average rate of change is equal to the instantaneous rate of change. Like my average speed had to be equal to the instantaneous speed at some point. So at some point in that interval, I was going exactly 80 miles per hour. Now, I found this very challenging as a Cal 1 student, trying to find these values of C that satisfy this on an interval. So let's do this together. And I have a process. First, let's calculate the slope of the secant line. Well, A equals 0, B equals 1. So we're talking about f at 1 minus f at 0 over 1 minus 0. Okay, what is f evaluated at 1? That's 1 squared, which is 1, plus 2 times 1 plus 1, that's 4. What is f at 0? That's just 1. So f of the slope of the secant line is 3. At some point in this interval, which is not very big, there's a place where the slope of the tangent line will also equal 3, and that's what we're trying to find. So we need to find the derivative. That would be 2x plus 2. So what is f prime at c? Well, we simply put c in for x. And it says set this equal to the slope of the secant line. And by this, it meant this. I don't know if that's entirely clear. So in other words, 2c plus 2 has to equal 3 somewhere. Then we solve for c. Well, that means 2c equals 1, and c must equal 1/2. So what does this mean? F prime of 1/2 equals 3. And you can check it for yourself. And 1/2 is in my interval. So I think I have a graph for us to look at. Okay, it's kind of hard to tell that this is the graph of x squared plus 2x plus 1. That's in the black. And here is 0. Here is 1. This is my closed interval, 0, 1. And here is c. c equals 1/2. And if you look, the purple line is the secant line between the point formed by 0 and 1. So in other words, from A, f at A to be f of b, that joining those 2 points. That's the secant line, the purple. And in the blue dots is the tangent line. And they are parallel. They have the same slope. So this is the point, C, in the interval, where the instantaneous rate of change is equal to the average rate of change over that interval. All right, let's try another one. Okay, so we're trying to find that value of C in this interval such that the slope of the secant line equals the slope of the tangent line. So first we find the slope of the secant line. So A equals 1, B equals 2. So we want f of B minus f of A over B, whoops, B minus A, which is 2 minus 1. So what is f of 2? That would be 2 plus a half, so we can call that 2.5. What is f at 1? Well, f at 1 would be 1 plus 1 over 1, which equals 2. So, what does the slope of the secant line look like? It's 0.5 over 1, which is 0.5, or if you prefer, like which I do, in this case, 1/2. So that's the slope of my secant line. Now we need to set that equal to the slope of the tangent line. So to do that, we first need the derivative. What does it look like? Well, you might want to rewrite f as x plus x to the negative 1. Then we see the derivative is going to be 1 minus x to the negative 2, which I think is easier to understand as 1 minus 1 over x squared. So what does f of c look like? We just put c in for x. So it's simply 1 over 1 minus 1 over c squared. And we're going to now solve for c. We have 1 minus 1 over c squared. Set that equal to 1/2. So we're setting f prime of c equal to the slope of the secant line. So how do we solve for c? Well, I would do this. I'm going to get c on one side and the numbers on the other to start with. So this would be 1 minus 1/2 equals 1 over c squared. In other words, 1/2 equals 1 over c squared. So c equals plus or minus the square root of 2. However, we are looking for a positive number in the interval 1, 2. So we are looking for c equals the square root of 2. So that is where the instantaneous rate of change is equal to the average rate of change in this interval 1, 2. So let's look at the graph for this one. We have in black f of x equals x plus 1 over x. In green dashes, this is the tangent line at x equal the square root of 2. Square root of 2 is right about here. Here is, well, we don't get to see the x-axis, so it's down here. So let me put the square root of 2 down there on the x-axis. This is here, square root of 2, right about here. Here's 1. Here's 2. Why did I write 1? My bad. Square root of 2. And here's 2. So there's my interval. The purple line is the secant line between the 2 points. Here we have 2, 2.5. There's that point. And here we have 1, 2. The purple line is the secant line. Its slope was equal to 1/2. And the slope of the tangent line there is also 1/2. And we could also say this, f prime at the square of the square root of 2 is 1/2. And you could check it. What is our derivative? F prime of x was 1 minus 1 over x squared. Well, plug in square root of 2, and you get 1 minus 1/2, which equals 1/2. So, I'm going to pause here because this is one of the main things that's new that you have to learn. You have 3 homework problems. Let's see if I told you which ones they were. Maybe on your handout. I think it's number 7, 8, and 9, where you're finding this value C. You're asked to do just this. So refer to the handout and try to work those problems and let me know if you have any questions. And then come back and watch the rest of the extreme value theorem. So bye for now. Extreme mean value theorem. You can tell it's late in the day and I'm very, very sleepy. All right, talk to you later.